So for the first talk of this session, we'll have Elena Asencio, who I had the pleasure of working with over many years in Bonn, and she'll be talking related to the previous talks on the tidal stability of Fornax Cluster dwarf galaxies. So I hope she'll go through in some detail, like how exactly tidal radii are supposed to be calculated in MOND.
I have 20 minutes.
Yeah. Okay. Well, all right. Well, I'll let you get started.
Hi everyone. So, like Indra was saying, I'm going to be talking about the tidal stability of Fornax Cluster dwarfs in Roman dynamics and in Newtonian dynamics. So, first thing I should be introducing is the Fornax cluster itself. So the Fornax cluster is the second closest galaxy cluster to us, only 20 megaparsecs away, and it contains dwarfs which have different masses and shapes. The Fornax Deep Survey catalog contains several of these dwarfs. Most of them are dwarf ellipticals and dwarf spheroidals, and one particularity of this survey is that it has a 50% completeness limit at an absolute magnitude of minus 10.5 and a surface brightness of 26 magnitudes per second. This survey was able to observe dwarfs which were significantly fainter with respect to previous surveys of the Fornax cluster. So as maybe you can see these three examples, the dwarfs in the Fornax Deep Survey catalog cluster are classified depending on their morphologies in very disturbed, mildly disturbed, and undisturbed. Like in the following analysis, we're just going to distinguish between disturbed and non-disturbed for simplifying things. So now the point of the whole analysis is trying to distinguish between MOND and Newtonian dynamics, or like specifically lambda CDM, by using the morphological structure of these dwarfs, like how disturbed they are. So how are we going to do this? So let's say you have your main galaxy there, and your dwarf is like very far away from it. So in the MOND case, you have that your dwarf is in the MOND regime, and its self-gravity is going to be enhanced with respect to the purely baryonic model because of the Mondian boost to its self-gravity. In the lambda CDM case, you also have that the self-gravity of the dwarf is enhanced because in the lambda CDM case you have this big dark matter halo surrounding your dwarf. Now, what happens if the dwarf gets close to the big galaxy? In the MOND case, what's going to happen is that the external field is going to dominate, and therefore, in the MOND case, the self-gravity of the dwarf is going to be more similar to the one it would have in the Newtonian case. In the dark matter scenario, your dwarf is still going to be surrounded by a dark matter halo, so same self-gravity. What we should get from this is that dwarf galaxies in the MOND case are going to be more susceptible to be disturbed than in lambda CDM, because in MOND they get this external field effect, and in lambda CDM they don't. And also in the lambda CDM case, you would need to first destroy the dark matter part before you can actually touch the baryonic part. So what kind of effects could be disturbing these dwarfs in the galaxy? First option would be round pressure stripping, but this seems very unlikely because the Fornax cluster is not very gas rich, so this seems unlikely. Second option is that you have big galaxies, your ellipticals, which are harassing or disturbing your dwarf galaxies. If this was the case, the disruption timescale would be given by this formula over there of Bonn and mean. And as you can see, the formula looks very similar in MOND and in lambda CDM. But of course, in lambda CDM, you would need to take into account that the mass has baryonic mass plus dark matter mass. And in the MOND case, you would need to take into account that your gravity is not Newtonian. You would need to account for the MOND effect. In this case, we're assuming the simple interpolating function, but yeah, this G effective is what accounts for that effect. Another possibility is that the dwarfs are being disturbed by the effect of the cluster tides. This is tidal disruption. In this case, the formula, the quantity that we should be interested in is the tidal radius, which is the radius starting from the center of the dwarf at which the effect of the clustered tidal field should overcome the self-gravity of the dwarf. So it also looks kind of similar in Landau-CDM and in MOND, except for some subtleties on how the gravitational potential works in MOND with respect to Landau-CDM. And as in the previous case, we also take into account that in Landau-CDM we have dark matter plus baryonic matter, and also for being conservative, we're just taking into account the dark matter within the optical radius, which is just 4% of the total dark matter mass, so we're being conservative here. And yeah, also in the MOND case, we take into account this correction to Newtonian gravity. And also to compare the dwarfs equally, we calculate this tidal radius at when the dwarfs are at pericenter for all dwarfs. So now that we have all these definitions for disruption timescale and our definitions for tidal radius, now we can actually calculate what is the tidal susceptibility of the dwarfs, depending on what is the phenomenon disturbing them. So let's say that they are being disturbed by harassment. In this case, we would need to compare the disruption timescale of the dwarf with the age of the dwarf, or how long has been the dwarf in this cluster. So if the disruption timescale is significantly larger than the age of the dwarf, the tidal susceptibility is going to be very small, so the dwarf would not be very affected by harassment in this case. And on the contrary, if the if the disruption timescale is significantly smaller than the age of the dwarf, your tidal susceptibility is going to be very high. So we're going also to the other possibility that the tidal susceptibility comes from the effect of the cluster tides. In this case, we would be comparing the half mass radius with the tidal radius. So let's say that your dwarf has very strong self-gravity, therefore your tidal radius is going to be very far away from the center, which means that your dwarf is not going to be very tidally susceptible. On the opposite case, you could assume, well, you could have this scenario in which your dwarf has very little self-gravity, therefore your tidal radius is going to be very close to the center, and therefore you will have that it's going to be very tidally susceptible. To the point where if your tidal radius is way, way smaller than your half mass radius, the dwarf is probably going to get destroyed. So now we have all our formulas defined, and therefore we can now just apply them to the dwarfs that are in the catalog. So these two histograms show the tidal susceptibility that you would get by harassment, applying the previous formula. As you might see, these tidal susceptibility values are very small, so it seems unlikely that harassment is the reason why these dwarfs look perturbed. So now we look to the tidal susceptibility from the cluster tidal field. And in this case, you might be able to see that the numbers are quite higher. So it seems like the reason why the dwarfs are being disturbed in the Fornax cluster case is because of tides from the cluster tidal field. So yeah, since the effect of tidal susceptibility by harassment is way smaller than the one from cluster tides, from now on in the analysis we're just going to be considering the tidal susceptibility from the cluster tidal field when we're talking about this. And also, as you might notice, the values of the tidal susceptibility are about 5 times higher in MOND than in lambda CDM. And as I was saying before, this is to be expected because dwarfs in MOND are more likely to be disturbed than in lambda CDM. Now, next thing that we do is we compare these tidal susceptibility values due to cluster tides. We compare this with whether these dwarfs were classified as visually disturbed or not in the catalog. So as you might be able to see in this graph over here, it does seem that the higher the tidal susceptibility calculated for the dwarf, the higher the probability that this dwarf is going to be classified as disturbed in the catalog. You might also be able to see that the trend goes up at values significantly higher in MOND than in lambda CDM. What we want to do now with this information is basically try to infer at which tidal susceptibility value do the dwarfs start being classified as perturbed in the catalog for each of these models. That is, we want to get to the minimum tidal susceptibility value. And we also would like to know what is the maximum tidal susceptibility value reached by the dwarfs before being destroyed in each of these models. So we would like to do this as accurately as possible and also trying to minimize as much as possible the projection effects. To do so, we constructed like this test particle simulation. We try out like all possible initial distances, all possible eccentricities, and yeah, we just set up the simulation. And yeah, we also considered all sky projected separation from all possible angles. Another thing about the simulation is that we would like it to look as similar as possible to our Fornax dwarf system. To do so, we assigned probabilities to each of these orbits in terms of its radius or distance to the center, its eccentricity, and we also assigned the probability to each of these orbits or dwarfs in the orbits to be classified as disturbed in terms of their tidal susceptibility values. Well, to do this, we left as free parameters all these. I'm not going to read all of them, but several parameters related to the distance of the orbit, the eccentricity of the orbit, and their probability of disturbance. And we apply the MCMC method. And basically, this triangular plot is just summarizing the best fit values for all the parameters that we left as pre-parameters. Among all these little boxes, I would like to focus on the little box that refers to the values of eta destruction and minimum eta disturbance that was fitted with this method. So as you can see from the results, in the MOND case, you would expect dwarfs to be destroyed when they have tidal susceptibilities like from 1 to 3.5 more or less. And in lambda CDM, which is that little orange thingy down there, you would expect the dwarfs to be destroyed when they have tidal susceptibilities which are like really, really, really small, like about 0.2 or something like that. And just to clarify, these are not necessarily the tidal susceptibilities of the dwarfs. These are the tidal susceptibilities that would be needed in order to explain the observations. But now we need to ask, like, at which tidal susceptibilities are the dwarfs actually expected to be destroyed, like, regardless of where they are, just when is it a realistic value for the eta in, yeah, you get it. So what we do to answer that question is we used n-body simulations. And in the case of the London CDM and body simulations, we just used the results from Peñarrubia 2009. And the embodied simulations said that dwarfs in Lambda CDM should get destroyed at eta about 1. And I just marked that like with this orange line on the previous plot. And as you can see, there's a big discrepancy between the value that they should have in order to match observations and the actual value at which these dwarfs should get destroyed. In the MOND case, we used the results of Asencio 2022. And in this, we saw that the dwarfs should get destroyed when they have a tidal sensibility of 1.7 plus minus 0.3, which, as you can see, is in very good agreement with the values that the dwarfs should have in order to match the observations. So, yeah, just to summarize. And so the observations of the Fornax dwarf morphologies tell us that they are disturbed, and also that this disturbance of the dwarfs is higher towards the center, and also because of this and because the other processes seem unlikely, we expect that the main process causing this is cluster tides. And also, like, intuitively speaking, one would expect that the dwarfs should be either destroyed or very disturbed when their tidal radius is about the same size as their half mass radius. That is, when their eta value is approximately 1. And what we found in the CDM is that the Fornax dwarfs should not be tidally disturbed given how small their tidal sensibility values are. But observations say that they are disturbed. Therefore, this would imply that in order to match observations, these lambda CDM dwarfs should be destroyed or severely disturbed when their tidal force is about 0.02 times its internal gravity, like ridiculously low. And in MOND, we find that the Fornax dwarfs are expected to be disturbed, given the fact that they have tidal susceptibilities which are rather high, especially compared to Lambda CDM. And this requires a tidal stability limit of 1.88 plus minus some error. And this is in very good agreement with embodied simulations, which imply that dwarfs in MOND should be destroyed at a tidal susceptibility of 1.7 plus minus 0.3. Yeah, that's all.
Any questions relating to this talk? So we'll take Federico.
Very nice work. So in galaxy clusters, there is a significant amount of intra-cluster light, which is typically interpreted as light coming indeed from the disruption of dwarf galaxies. So I was wondering whether you can use your simulation to have an estimate of what the amount of intra-cluster light should be in MOND as well as lambda CDM, so that can be directly compared with observations.
I mean,
maybe basically the graph is dwarfs above this red line. If you estimate how many there would be.
no, I mean, but when you say intracluster light, you mean like simulating how much contamination there would be, or?
So I'm saying that in clusters there is some light which is not associated to galaxies.
Mm-hmm.
So the idea is that those are individual stars that have been stripped out of galaxies.
Mm-hmm.
So this is pretty much consistent with what you are suggesting, that these objects are tidally disturbed and the stars have to go somewhere, and then will go orbiting the potential of the cluster. So I'm just asking, or it's a suggestion for future work, if you like, whether it may be possible to quantify how much of this intercluster light should be.
I mean, I'm assuming that for that you would need like a detailed simulation, not just a point mass simulation. So I guess one would need to like do the simulations like in more detail than this was done. So I mean, it's a nice suggestion for the future.
I think Aku has done this.
Yeah.
Aku has done this. I'm not sure what the answer is.
Hi, I'm wondering how much the tidal susceptibilities in MOND would change if you imagined that there was no EFE, or in other words, to what extent does your analysis provide evidence for the EFE in MOND?
So, I mean, we didn't do the experiment, so I don't have like a super clear answer, but I mean, definitely they would be less tidally susceptible. I don't know how they would compare to Lancerium in that case, but yeah, it would
So
be
do you
significantly
think
reduced.
they would then disagree with the expected results, or it's not
I mean, it's hard to tell without actually doing the calculations. But yeah, I mean, I still think they would maybe be a bit higher than the CDM, I think. But I mean, we would need to do it to actually confirm it, like.
Thanks.
Yeah.
So can I borrow this? Yeah, so it would be, without the EFE, there would be a significant difference, because if you're in the regime where tides are, where you're at the tidal radius, then by definition the EFE must be dominant, because if the tides across the object are already more than the internal gravity, then the total cluster gravity must be a lot more than the internal gravity. So I think there would be a significant difference, and in that case the dwarfs would be a lot less tidally susceptible. I don't know whether that would agree with, whether that would violate the agreement with observations you had here. Right, were there any more questions? Here. Sorry, we'll take.
So I was just wondering if you have any kind of like plans for future work, or I guess what you would do next, or if you think there's something to do next in this topic.
So there was like the idea of trying something similar with local group dwarfs, but I'm also now focusing on another project. So I think Srikam was working to work on something like this, maybe, I think. So maybe I don't do the work myself, but there are like plans to also keep working on this.
I guess you could probably do this with other clusters too, as long as they're not too far away.
Yeah, I mean, you also need to be like a bit close to have properties, otherwise, yeah.
Thank you.
Thank you.
Yeah, so you had a quick question, what do you?
Just wonder if you could say something about comparing with the coma, for example. Would harassment be much more important in the coma? Important enough to...
Yeah, I mean, if I remember correctly, like Jonathan did something like this, I think.
Srikan's work assumed the smooth they have a potential for calculating tidal effect, but there should also be, at some level, there should be some harassment, which I was just wondering if it's probably more important than in Fornax.
Yes, it's probably more
The
important than in the Fornax
density,
case, yes.
higher density galaxy could also be gas stripping.
Yeah, I mean, it's definitely a possibility, and it would be an interesting project to try that out, yeah.
Yes, it's not possible to answer this question at this stage in detail if the tide harassment scenario would be relatively more important than tides in the coma cluster, but that's an important consideration if trying to repeat this in the coma case. Right, yes, Sanjay?
Can I see the opposite inside a galaxy? A star cluster would, in MOND, be less susceptible than their CDM, in living in a CDM. the MOND protects the star clusters a little bit, depending on how dense the star cluster is. But the MOND protects it. I'm saying the trend should go opposite. If the same physics plays, the trend should go opposite in galaxies than in galaxy clusters. And it'd be good to see a comparison study.
Yeah, yes, this has actually, this is correct, because star clusters should not have their own dark matter halos. The main difference here is, of course, that dwarfs were being protected supposedly by dark halos in MOND.
Is that you were able to talk, or is it a discussion?
No, I was addressing this
Yeah, you
question.
were addressing that, but sir.
Yeah, you know, with respect, the speaker did ask Indranil to answer that question for her.
One thing I wanted to point out regarding this, you are correct that the trend should go opposite. But there was a study on this by Pavel, right? You want to answer about that?
Yeah, about the star clusters.
Yes.
Yeah, I mean, what I found is also like this more like signal in the sense that the matter distribution was asymmetrical because of the different potential in MOND. But I don't know if you have a question.
No, I'm just saying it's good to do a comparison study in two environments.
That would be an interesting project. I don't believe that has been done yet.
No, it hasn't been done.
Any, just one last question from anyone? All right, so I guess we'll hand over to Mikhail Vilek for a start.